Okay, so let's move on to discuss a few new concepts. It's the concept of a sequence, the concept of a recurrence relation, and then some formalism for representing summations. So previously we saw that while sets are inherently unordered, we can produce sets of ordered pairs using the idea of a Cartesian product. So now we're going to introduce the idea of a sequence, which intuitively is an ordered list. A to-do list in which the order of the tasks matters would be a perfectly good example of a sequence. But most examples of sequences we will use are lists of numbers. A sequence is at bottom a certain kind of function. And the definition of a sequence is as follows. A sequence is a function from a subset of the set of integers, which we normally represent as z, capital Z, to another set, S. So rather than using the notation f of x, which is familiar to us, we use the notation an, or sometimes an with parentheses around it, where n represents a specific integer. Now, of course, strictly speaking, the set of integers is unordered, as is the codomain of this sort of function. So when we say that a sequence is essentially an ordered list, we're cheating a little bit here. The order is really the order we naturally associate with the integers. So, for example, using our familiar notation, the f of x notation, we could define a function like f of x equals x plus 1, and we know how to calculate any value of x for that. However, when we write the function this way, a sub n equals n plus 1, with or without parentheses, it refers to the ordered sequence 1, 2, 3, etc. And that's because when we plug 0 in for n, we get 0 plus 1, which is 1. When we plug 1 in for n, we get 1 plus 1, which is 2, etc. So as I note, this formalism actually departs from the formalism in the text. The text uses set brackets to define sequences, and this is actually not normal, and it's also a little bit confusing since we have been quite emphatic that sets are not ordered. So philosophy students are familiar with David Hume's problem of induction. So Hume argued that it is impossible to know on purely logical grounds that a particular pattern we have observed or think we've been observing until some moment in time will continue after that moment in time. So this applies to mathematical contexts as well. If we specify a sequence in this manner on the set of positive integers, say z plus equals 1, 2, 3, etc., a to the n equals n plus n squared, then we've been given a rule, and we can derive the extension of this set by simply applying it. We know this set follows the rule because we are using the rule to generate it. So an equals, we know, 2, 6, 12, 20, 30, etc. And in this case, of course, it would be because we defined the sequence on the positive integers, not the natural numbers, which often or normally include 0. So our first n would be 1, right? So 1 plus 1 squared is 2. Our second n would be 2, and so 2 plus 2 squared is 4, is 6, etc. Okay, I know these are trivial calculations for those of you who are taking math classes all the time, but they aren't trivial for everybody in the class. However, if we identify a set by its extension, so 2, 6, 12, 20, 30, and you may have caught that I should have said list here, not set, and then are directed to derive the rule or function that generates it, we cannot do it with certainty. If we tried for a while and came up with an equals n plus n squared, we might be convinced by the fact that it predicts this segment of its sequence that it has to be the right answer. But there is, in fact, an infinite number of functions it could be. To see this, just imagine specifying a function that actually does follow n plus n squared up until the last two members are multiples of 10, and then begins just by counting by tens. Hume simply applied this simple point about math to nature itself. So one of the main reasons for studying sequences is to become acquainted with the idea of a recursive definition. Recursion is a very important idea in logic and computer science, and it's philosophically interesting as well. It's widely thought to be one of the essential mechanisms in the development of natural language. The word recursion refers to the fact that the definition of the function is built on a previous element of the sequence. In other words, in order to find some value a sub n, you need to know the previous value a sub n minus 1, the previous member of the sequence. The function a sub n equals n plus 1 on the natural numbers is non-recursive. You can find the value for n equals 7 by simply computing 7 plus 1. Formulas like this are called closed formulas because they involve doing a fixed operation or set of operations on n itself. Just about every mathematical formula you have ever had to memorize for a math or physics test is a closed formula. On the other hand, this function, a sub n equals a sub n minus 1 plus 1, is not closed. This is because to compute the value for, say, n equals 7, you must already know the value for n minus 1, which is 6. So the previous value recurs in the definition, which is why it is called a recursive definition. So this isn't put quite optimally. The idea is that not so much that the previous value recurs, but that in relying on a previous value, we're essentially relying on an, because the previous value is defined in terms of an. So effectively an is what's recurring. So far, a philosopher who is unfamiliar with recursion would be justified in wondering why this isn't a circular definition, meaning one that is perfectly uninformative and useless because it defines a term by using that very term in the definition itself. Philosophers are typically counseled that this is typically a fallacious thing to do. Well, this is a slight overstatement. A recurrence relation that fails to state initial conditions still puts a very strict conditions on what can count as a solution to it. However, without specifying such conditions, what is true is that it will admit of an infinite number of solutions. And this means that until we provide initial conditions, a recurrence relation like an equals an minus 1 plus 1 is not a function at all. Hence, for a recursive definition to specify a function by means of a recurrence relation, it must provide a specific value for the first member of the sequence, commonly called the initial condition, and it's typically defined as a sub 0. So the definition of a recurrence relation is this: a recurrence relation for the sequence a sub n expresses the value of any an other than the initial condition in terms of one or more previous terms of the sequence. And for the initial condition AO, a specified value must be provided. So recurrence relations will in fact often make reference to multiple previous terms of the sequence, and in such cases multiple initial conditions will be stated non-recursively. So a famous example of this is the Fibonacci numbers, which is a sequence that's generated by adding the two previous numbers in the sequence. So that means to be able to write down the sequence, you're going to have to at least be given the first two numbers. So if, for example, we're given 0 and 1, then we're off to the races. We've got 0, 1, 1, and 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, etc. So this sequence can be recursively defined on the positive integers like this: an equals an minus 2 plus an minus 1. So there's two initial conditions that must be specified: AO equals 0 and A1 equals 1, and this of course generates that sequence. Now you might guess that functions that are defined recursively must be defined recursively, but that's not actually the case. Recurrence relations can often be solved, which means that they can be represented as closed formulas. The closed formula expression of the Fibonacci sequence is this. I won't read it, but you can see that it's rather complicated, and this gives you a reason or an understanding of why it can sometimes be preferable to have a recursive definition. Clearly, the recursive definition of the Fibonacci sequence is much more elegant than the closed formula. However, using the recurrence relation to compute a particular member of the Fibonacci sequence requires knowing the two previous values, whereas the closed formula does not. And this is a big deal when humans are doing the calculating. So these days, a pocket calculator can easily use a recursive definition to compute the first million members of the Fibonacci sequence in the time it takes a human to use the closed formula to compute just one of them, which is one reason why recursive definitions are so useful in computer programming. So Hume's problem of induction has an interesting application here as well. Mathematicians use lots of methods for attempting to discover closed formula equivalents of recurrence relations. One method, one of the simplest methods, is known as iteration. Basically, this just consists in solving the recursive formula for successive values until you are lucky enough to notice a pattern. Okay? So if you consider the following recurrence relation, an equals an minus 1 plus n. So there's the reference to the previous element of the sequence. And AO equals 4, that's the specification of the initial condition. Then we can easily compute this recurrence relation. So we know that AO equals 4. So 4 is the first member of the sequence. So that's AO, right? The second member of the sequence is going to be A1. The third member will be A2, etc. So to compute A1, we know that A1 is identical to an minus 1, which in this case is A0, plus n. So n is 1, so 4 plus n is 5. And by the same reasoning, A2 is going to be n minus 1, which is now 5, plus n, which is now 2. So that's going to be 7. And you get the idea. So the sequence is easily computed. So then what a mathematician wants to know is whether there's an equivalent closed formula. Well, if you look at what is happening here, you can see that for any given an, the corresponding number is greater than its immediate predecessor by the value of n that generated it. And that's actually sort of a complicated way of saying that if you look at 10, for example, you can see that 10 minus 7 is 3. 7 minus 5 is 2. 5 minus 4 is 1. And really, that just amounts to rearranging this formula so that it says an minus an minus 1 plus, equals n. So an minus 1 equals n. And you can stack all the individual computations like this if you like. A1 minus AO equals 1, A2 minus AO equals 2, etc. So that you generate the numbers 1, 2, 3, 4, and 5. Then you know that this plus this plus this plus this plus this equals 1 plus 2 plus 3 plus 4 plus 5. So you might come up with a formula representing the sum of all of these and a formula representing the sum of all these as individual sequences. So on the left-hand side, you can see that you get a lot of cancellations. We have A1 minus A1, A2 minus A2, right? A3 minus A3, A4 minus A4, and you're left with A5 minus A0. And of course, we just arbitrarily stopped at 5 here, so that would actually be AN minus A0. And then if you have taken a little math, which of course many of us have not, and even if we did, we might have forgotten, but there is a famous closed formula representation of 1 plus 2 plus 3 plus 4 plus 5, etc. And we won't bother to prove it, but the formula is n times n plus 1 over 2. That's the closed formula representation of the sum of the first n numbers of this particular sequence, 1 plus 2 plus 3 plus 4 plus 5. So what that just means is that if you plugged in, if you wanted to know, for example, what 1 plus 2 plus 3 plus 4 plus 5 is, you would simply plug 5 in for n, and then you would multiply it by 6. So 5 times 6 is 30. Divide it by 2, and you would get 15. And sure enough, if you count it, if you sum it, 1, 2, 3, 4, 5 equals 15. Okay, so you get this identity. Nobody's holding our hand to help us figure this out, of course. It's just somebody noodles around until they see this relationship. But that's the process, one of the simpler processes for figuring out a closed formula. So since A5 was the last member of the sequence we chose to represent on the previous slide, and AO is the initial condition, which is defined as 4, the formula we've just derived would be A5 minus AO equals n times n plus 1 over 2. Stick in 4, right? For AO, we have AN minus 4 equals n times n plus 1 over 2. And so AN equals n times n plus 1 over 2 minus 4. And we have now produced a closed formula representation of the recursive formula. And you can see that this minus 4 is still letting us know what that initial condition was. So we won't work through any more problems like this. It's what you would spend time doing in a discrete math course. But it's important to see that what we've done here does not constitute a proof that the closed formula is identical to the recurrence relation. We've done significant calculations, but these are all based on the initial guess that the pattern we think we've discerned is real and that it will necessarily continue, as we were explaining before. So it seems obvious to us that it will, but this is something that has to be proven by a technique that we call mathematical induction, which is actually a deductive technique, confusingly, that we will discuss later. So of course we could test our result just by substituting it into the recurrence relation as we did previously. But again, this is only a viable proof of identity if we know the recurrence relation itself can be depended upon to continue in this manner. So one way or the other, mathematical induction would be required to actually prove that this closed formula was correct. Now, to finish up, sometimes we want to add up the first n members of a sequence, and to represent this sum, we just use the summation sign, which you're probably familiar with. So if we just write down the formula for any given sequence in this capital Greek letter sigma with j equals m on the bottom and n on the top is the summation sign, and it just tells you that your initial j is some number, say in this case just m, right? And you're summing everything from m to n. So down below, an example would be the formula I squared, right? The sum, if that's represented as sum a to the n, then we're looking for the sum of a particular sequence. So beginning with I equals 1 and continuing to 5, we'd have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared equals 55. And we can also use this summation sign to express the sum of the members of an unordered set. So we could just say S is an element of S, and we could say sum up all the elements of S according to some formula f of S. So for S equals, say, the set 1, 7, 9, and f of S equals x squared, we could write it like this. S equals the set 179 x squared, and this would represent this sum. All right, so that's an introduction to different ways of representing important concepts of sequence and recurrence relations.